Good morning. Welcome to the second day. And we'll begin with a round of talks. First, we have Hyunsoo from Princeton, and he was going to present the outcomes of a recent RQS seed grant related to quantum simulation of non-equilibrium coarsening dynamics with applications to adiabatic algorithms.
Thank you so much. Can everyone hear me? Good. Before I start, I want to appreciate everyone who's in the audience because I'm personally not a morning person, so it's really hard for me to wake up early. So thanks for everyone being here. Today I'll talk about quantum simulation of non-equilibrium coarsening dynamics with application to adiabatic algorithms. They have a lot of words, but mainly you can think today I'm talking about the coarsening dynamics and some interesting many-body dynamics that could be, you're proposing what is an interesting physics we can see in these quantum simulation devices. And I should also appreciate my collaborators, Professor David Hughes and Rhine Samajdar. So what can we do with the quantum devices today? We are still struggling what we can do. And Feynman actually guided us to what we should do many decades ago. And he thought about we maybe have to do quantum simulations. And reminding what Feynman told us, we as a modern physicist also thought about what quantum simulation we can have fun with. And we came up with we should do many-body dynamics. And I think a lot of people will agree that many-body dynamics is a thing to work on in near-term quantum simulations. There are a lot of many-body dynamics, and today I'm going to specifically talk about the coarsening dynamics. So what is a coarsening dynamics? Coarsening dynamics, you could think about having a lot of domains and domain walls between those domains, and how these domains and domain walls evolve over time. So this isn't one example of coarsening dynamics. This concept was a very old concept. They're shouting out for every big giants here. And it will be immediately understandable if I show you some examples. So at the very beginning, we'll start with a bunch of dirty blacks and white domains. But as time goes by, small domains are meet together, and they go into they become large domains. So a lot of small domains are. There are a lot of types of coarsening dynamics, and this is one example. But one thing to note is coarsening dynamics could be viewed as a lot of small domains eating up together and trying to make a large domains. So before I was involved in all these projects, Ryan and David had a theory on how can coarsening dynamics have a role in ramping our state. So we do a lot of we have to ramp our state when we do the state preparation. For example, we have a disorder. So this is something this is called Hibbels-Rank mechanisms. So you're starting from a simply preparable state, and you're ramping your Hamiltonian to maybe a critical Hamiltonian or some different Hamiltonian, and see how these states evolve over time. Hibble and Zurich, who are also other giants, thought about some scalings that involve on these rampings, but Ryan and David thought about maybe other than Hibble-Zurich, the coarsening dynamics can also play the role, and they made some scenarios how they make some interplays. And this is the theory work. And there is a recent experimental work by Harvard, and also Google have a similar work too, but forgot to put the Google's work. And so they look into the quantum coarsening that was predicted in theory. And also, one interesting thing they figured out was while they were trying to understand experimentally on quantum coarsening, they also figured out some new dynamics, which is Higgs mode. And their model was 2+1D transverse field sizing model, so it's like a quantum magnet. And they figured out there are some weird oscillations going on. So this also motivated us to work on some related works. I will talk about it later. So what will I talk today? In this talk, because the main theme is the coarsening dynamics, we are asking, can this coarsening robust under noise? The high dimension is too hard. As a theorist, we start with a very basic, simple example, so we'll work on one-dimensional models. But we make a clear understanding what is different between bits and Potts model. Or you can also understand this as a Q bits and Q dits, or Q trits. So the model the phenomena what we are actually working on is absorbing state transition in one dimension, which I will also define later. And from the lesson we learned from this classical absorbing state transition, we draw some analogy to the passive error correction and repetition code. Some might think it is a silly thing to do because 1D repetition code really is not a passive. It's already known it could not be like fault tolerance, but there are some lessons we learned I want to share with you related to the course in the perspective of coarsenings. The second part of the talk, I'll talk about the Higgs resonance, which was motivated by the experiments. But again, the simplest model is one dimension, so some one-dimensional models. And it has a lot of similarity with the Higgs mode, but we figure out there are some other mechanisms that could have some similar oscillations. So these are the key parts I'll talk about today in this talk. And also, feel free to ask questions if you have any. Okay, so this is the first part of my talk. So we go back to the classical coarsening in one dimension. I'm trying to understand the most simplest example we can think of. And as I told you, I'm thinking of the absorbing state transition. The absorbing state, what is an absorbing state? Absorbing state is, let's think about starting with any random initial bits, like zeros, ones, or ups and downs. And we have a goal to get into the target state. And the target state here is, I want all the bits to be all ordered up or ordered to be down. And once you're inside the absorbing state, as a definition of absorbing state, you cannot get out of the state. To reach the absorbing state from any random initial bits, for example, ups and downs, what we can do is we have to clean up all the domain walls. And this is actually the coarsening. And also some weird thing about the domain wall is you cannot just delete a single domain wall. Domain wall always have to annihilate by pairs. So you have the orange domain at the side, and you have the blue domain in the middle, and you have a two domain wall in between. And what I will do in my local rule is I will let them domain wall to random walk. And as they random walk, they'll meet the pairs and they'll all annihilate. So this is a coarsening to get into the target state. However, I'm interested in how robust it is under the noise. So the noise model is you're being too ambitious. So we want the domain wall to random walk. And to random walk, you just flip a single spin right next to you. However, if you flip both spins right next to you, which have a red colors, you may sometimes introduce two more domain walls, so you're screwed up. Because we want to clean up all the domain walls, but sometimes if you make some noise and if you make some mistakes, with some probability P, you can increase the number of domain walls. So what we are actually doing is understanding the competition between the coarsening and the branching event that increased the domain number. So let's try to draw the phase diagram. So this is a horizontal line with branching rate of P. And if we know it is trivial that if we do not have any branching, everything will coarsen down. So in polynomial time, we will get into the target state. What happens if we have what happens if the P is not exactly 0? What is known is there is a critical point where you make a lot of noise over the threshold. you may never be absorbed into the absorbing state. So you never get into the target state you want to prepare. So this figure shows even a single defect is too detrimental. So they spread out with these gray areas, which is sum of all these small domains. However, luckily, if our noise is less than the threshold, we are able to, it is almost the same as the absorbing fixed point, which is p equals to 0. And we are able to approach you're able to approach within the polynomial time. And there are some weird lessons we learned here. What happens if so the phase diagram above is for qubits or bits, classical bits. What happens if we have like 3-pass model? So we have, instead of having zeros and ones, we're having zeros and 1 and 2. Can we do exactly the same thing? And also, pass and bits are a lot different, so shall we have some different universality class in the critical point? Actually, for a pass model, we figure out there are no robust absorbing phase, and you're always screwed up. So it was a surprise for us, and we should, as a theorist, we have to understand why it's going on. So the fundamental difference between 2-state and 3-state is they have some different type of domain walls. In 2-state model, they have a single type of domain wall. So, and the number of the total domain wall is preserved over like modulo 2. But in 3 states, you have some different types of domain wall, and the minimal branching event is like one domain wall branching to 2 different type of domain wall. And if I ask, how long does it take after a single branching event, and let's assume there's no any branching after that, how long does it take to become a single domain wall? If I ask the question, for 2-state, we have to only wait for a finite times, but for 3 states, it have a probability distribution that has a very thick tail. So because they're very close together, they will meet together with high probability, but the probability for two domain walls to not meet is also significant, so that you have a infinite expectation value for times of a time to meet together is infinite. So this was a argument we made why for the 3-state branching is always relevant, and you do not have a absorbing phase. The motivation for this is we were trying to, I was at the very beginning when I didn't know anything about quantum error correction, I was very ambitious to, can we use this coarsening as a resource to make a passive error corrections? So everything was classical, but if we do the classical rule on quantum bits, because if we can, in quantum systems, we have a superpositions. So in classical, you can go into like one of the ups and downs, but we can go to any point in the block sphere defined on all ups and all downs if we apply the same rule on the quantum bits, if things are absorbing. So starting from a quantum repetition code, and think of a bit flip errors, this defines a very dirty initial state. And if we act the classical rule, which I just described to you, then we will get into it. So like, can we use this as a resource to get into the fault tolerant, passive error correction scheme? But this is actually not true, because if everything is coarsening, then you cannot suppress the logical errors even though your system size is large. So even though you're able to absorb, you cannot actually have a logical error being suppressed. So that is why it cannot be used as a passive error correction, only using the local terms. However, if I allow some non-local information, so this is what we always do in the active error correction, you use all the data on the syndromes, you can actually suppress the error rate. However, this is also not fault tolerant, because along our classical rules, there might be another bit flip errors, and it might be very detrimental to have a bit flip errors while you're fixing it. So it doesn't mean it is like fault tolerant, even though we're using non-local information. So this is kind of open question. What are the minimal conditions we need to use to have a passive error correction schemes? And changing our gear, there was a interesting experiment by Harvard. They saw very weird oscillations. The different colors are showing different parameter regimes, and the parameter is a critical when it is in the gray area. Even in the gray area, they had the oscillations. And motivated by this, we are also thinking of some Higgs, which is excitations that has the same symmetry with the Hamiltonian. And we also want to be critical. That means we don't have any gap in the Hamiltonian. So one nice example is XXC spin chains, which is gapless when the parameter delta is between -1 and 1. And we use the quench protocol, which is we prepare a state which is a ground state from different deltas and evolve over time in a delta F Hamiltonian. So this is a way to investigate the spectrum of Hamiltonian with delta F. We also use the probe that has the same symmetry with the Hamiltonian. And this is the result. We see very clear oscillations. And the period has 2.15, 1 over j, which is omega's 2.5 j's. I'll take a note on that. This is not the trivial oscillations. This is not the Rabi oscillation. This is not what we expected. And we also try to understand what's the origin of this kind of new oscillations. And we figure out this is due to the von Hoff singularity, which is not a usual Higgs mode mechanisms. So let's think about the simplest model, which is free fermion when delta is exactly 0. Free fermion, the ground state is filling all the Fermi C. But we figured out the excitations that was involved for this probe was having 2 holes and having 2 particles. Because we have 4 particles, we have 4 momentums. But the total momentum should be 0, so we have 3 parameters. And if I draw in the 3 parameter regime, with the fixed values of energy, if I count the number of excitations, these surfaces show what are the valid excitations that can happen for P, Q, and large Q. You can see there is a change on the morphology. And that is when we have a von Hoff singularities. So the density of state, the horizontal axis shows the energy scale, and the vertical axis shows the density of state for that specific energy. And as you can see, because the morphology changes, we have a singularity in the density of state, which was nearby 2.6, which was almost the same as what the oscillation we saw. So, and this is for free fermions, but we're trying to extend to XXC models, generic XXC models using the Bayesian logic equations. The conclusion, we work on coarsenings and how it is robust under noise, which we motivated to understand these absorbing state transitions. And also we proposed to see some interesting physics in experiments, for example, like molecular systems. Thank you. Any questions?
We have questions?
Okay. Sorry, could you explain again what the manifolds are again? What?
So the excitations that are involved have 4 particles. So 4 particle means 4 momentums, but excitations should also have momentum 0. So 4 momentums, but momentum 0 we have 3 momentums, and 3 momentums define a 3D volume. In that volume, I'm counting what are the valid excitations that have the same energy, which is the horizontal line. So you fix the energy and you count all the excitations that have the same energy. So these surfaces are the valid excitations that have a fixed energy.
And the light blue, that's the fixed energy, and the dark blue is the valid excitations.
Light blue is it's like a brilliant zone.
Last question.
It seems there are many free fermion models of von Hoff singularity, like 2-dimensional time-bounded model.
I can't hear you.
So I'm just wondering the phenomenon, this oscillation you see, is a generic property for any model?
If I have a well-defined quasi-particles And if I really understand all the dispersion of the quasi-particles, then I expect to see such a oscillations. But you have to pick the right probe. So any probe might not work. You have to specify the correct probe to see these oscillations. So for example, this probe is involving with 4 particles. So you need the probe that actually, probing like 4 particles, for example.
Okay, let's thank the speaker again.